Welcome everybody and thank you for being here. So that's the final colloquium of the Chaire on materials innovation, on innovation technology, which was devoted to materials science, from material by chance to material by design. And I've chosen the topic of this meeting, filling gap in material space, method and applications. Okay, so just before we start, I want to put that in perspective with both the lectures which have been taking place during 9 weeks in Collège de France along the theme, but also in the tradition of Collège de France. The Collège de France is a multidisciplinary field, a multidisciplinary house in which there are people from very different fields which are coexisting and sometime interacting. Material science is by itself a cross-disciplinary field, but I wanted to have in this conference to have an opportunity of having people from biological sciences and people from material science to meet together. So that's the reason of the potpourri that you will have tomorrow, various cases of materials, materials from the engineer and materials from nature. Now, the topic I'm going to do today is introduce the lectures of the 2 days. So my topic is filling gaps in material science, challenges and method. So the general outline of the course was the following one. It was starting from just a brief statement of the evolution of material science since the beginning of prehistoric time towards nowadays, which was a progressive evolution from material you would find by chance, you would pick that on the ground, to material that you are now designing to fulfill a set of requirements. And this evolution from material by chance to material by design goes together with an increased multifunctionality in materials and with an increased importance of modeling in order to explore the space we have opened by the various possibilities of creating new materials. So the outline of the course was the following one. That was a sort of overview of the strategies to obtain high-performance materials. So I'm not going again to do the whole series of lectures. I just wanted to put that in perspective because today we are just going to look at 2 cases for which we are going to use all the lectures, all the topics which were introduced during the 9 weeks. And these 2 topics will be architectural material and bio-inspired material. But that will be understood in the general sense, which means that we will also look at the way of designing microstructure. We will also look at the way of processing the material. So the idea is to say, when we have a gap in the space of material, what are the possibilities to fill this gap, making use of all what we already know in material science, and identifying what are the topics which have still to be explored. Now, the materials family we are going to explore are these ones, of course. Of course, naturally, there is always a slight bias towards metals. I cannot really apologize for that. I love metals, okay? But what we try to do here is something which is generic of the various aspects. And we'll try to look at the ways of combining materials, combining geometries, in order to obtain properties that otherwise wouldn't be possible by a simple bulk material. Now, the key word here is Swiss cheese. The material space is a Swiss cheese with big holes and regions which are sparsely populated. So what we want to do is fill this Swiss cheese. And I'm going to show you the first sandwich of the series of lectures, which is this one. The examples I'm going to give are stuffed between 2 skins of sandwiches. The first one is how can we fill the holes, and the second one is do we really want to fill the holes? And between these 2 questions, we'll try to look what can be coming from microstructure design, from associating materials, the case of composites, from architectural materials, the playing with geometry, mixing the various strategies, and finally the bio-inspiration. So that's the stuff of the sandwich here. Now, each of these topics will be treated more in detail, either by today's presentation, which are very much on the method, or tomorrow's presentation, which will be very much on examples. Now, the microstructure design, let's look at the first contradiction we want to fill. That's a famous curve, which I used to call the banana curve. So we start from sandwich, we go on with banana. All that is becoming very gastronomical. The banana curve is the counter correlation between the elongation and the yield strength in material. And here it's focused on one of my favorite materials, which is steels. And here you find when a material which has a high ductility has usually a low yield strength, idea of steels, and a material with high yield strength has generally a low ductility, which is the case of martensitic steel. And the whole dream of scientists in the steel metallurgy is to escape from this banana curve and try to develop material which would have a good combination between ductility and strength. Now, the standard way of doing that is to play with the microstructure. So the metallurgist's dilemma being to combine strength and ductility, which are really usually contradictory. How can microstructure design find a compromise? Now, the reason for which there is a contradiction has a very deep physical basis, which is the following one. When you look at the plastic deformation of a material which has some plasticity, you have the yield stress, which tells you when you start to plastify. And of course, when the material starts to plastify, its stiffness becomes lower. The increase in stress to get an increased strain is smaller than what you have in the elastic regime. And this is called the work hardening. Now, if you look at the possible localization of deformation, if in some region of the sample that you are putting in tension, the deformation gets more localized, at this point you have a higher yield stress, of course, but you have also a lower section. If the increase in flow stress, which is basically related to the work hardening, cannot match the increase in local stress, which is a reduction in section, then you will get into trouble. And get into trouble means the localization of deformation will go on forever and will lead to a rapid failure. So that means that any material which has a high yield strength, which will favor the stress localization, where you have a change in thickness of the sample, will need a high work hardening in order to spread the plasticity instead of localizing it. So that's the intrinsic reason for which a ductile material, the stronger is a ductile material, the less is the ductility. You have another reason for that, which is if you have a pre-existing crack, this crack to propagate needs to dissipate energy, and the region in which it dissipates energy is much smaller when the yield stress is higher. So the result is that the crack propagation takes less energy. So these two reasons are the physical basis of the contradiction between strength and ductility. Now, one way of bypassing that is to use composite material, which means to use materials which have a phase which deforms plastically and a phase which doesn't deform plastically. The net result is that you create a back stress which is giving you an apparent work hardening. So you are not changing the yield stress, you are changing the work hardening. Now that's something which came from the composite material, but which is reused in classical material, which are called the dual phase steels. So the dual phase steels is basically a material which is a natural version of the composite material. Natural meaning that you don't mix the inclusion inside the matrix. So there are steels with martensite island, which are coming from quenched austenite. They are embedded into a polycrystalline ferritic matrix. The matrix deforms plastically. The martensite is elastic fragile, and that's a natural composite. Now, depending on the thermomechanical treatment, you can change the volume fraction, the hardness, the shape, the scale of the various phases. And that's going to give you some tools for material by design, designing this composite from the process of the microstructure. Now, here is the microstructure, okay? You have this mixture of ferrite and martensite. And now, what I want to show you is the kind of optimization you can get. So that's coming from micromechanics modeling of the behavior of the ferrite plus martensite mixture, and the ferrite behavior depends also on the ferrite grain size. And what you can find is that depending if you want a maximum energy absorption or if you want a maximum resistance with a ductility which is at least 8%, which are typical set of requirements for this kind of materials, this kind of modeling is going to give you what is the best content in carbon, what is the best volume fraction of martensite, what is the best grain size in ferrite. So you see what we have done here is designing a material which is tailored in order to meet a requirement which would be difficult if we wouldn't have this mixture effect. Now let's go to composite material, the most classical composite material. What I want to show you now is two examples. An example which is a selection map for light and stiff material, in which you would have a mixture between metals and ceramics, which is a classical metal matrix composite. Here this mixture would be, for instance, between titanium alloy and carbon fibers. And these two materials here, titanium alloy, which is represented in this place here, that's a diagram with the Young modulus and the density. The carbon fibers are here, and the properties of the mixture between titanium alloy and carbon fibers will lie somewhere here. These boundaries are given by micromechanics model, and this maximum here is given by the process ability, which is how much carbon fibers can you introduce into a titanium alloy. So here you will have different ways of making mixtures of carbon, of titanium or any sort of alloy with ceramics, and these mixtures will give you what are materials which would have a better, say, e to the 1/2 divided by rho property, which would give you the stiffness at minimum weight for a plate, for instance. Now, that's what we call the standard composite. Here, of course, it's purely theoretical because you need to know what is the effect of the mixture between the ceramic and the material, and one ever-coming problem will be the interface between both of them. And we'll have a number of talks about the role of interface into the properties of materials, of hybrid materials. Now I want to give you another type of composite, which is a bit more sophisticated, that a composite which is developed for high magnetic design, high field magnetic design. So these materials are wires, they need to conduct electricity, and they are winded around an electromagnet. And what you want to do is to make very high magnetic field, which means that you have pulse fields, which means that you are releasing a large amount of current in a very short time, which in order to reach magnetic fields which are of the order of 30 Teslas or something like that. They are enormous, which means that you are confining a material field inside a finite space, and this confinement in the finite space gives you a high magnetic pressure. And this high magnetic pressure is really a force on the winding, which might destroy the winding. Now, you need to contain the magnetic field without fracture. That gives you a first criteria between the yield stress and the field that you want to obtain. And of course, you don't want to heat too much, and that requires to have a high conductivity material, and gives you another maximum field you can reach, which is related to the thermal conductivity, to the diffusivity, and to the electric conductivity of the material. These two combinations of properties are performance indices, which will tell you if the material is suitable to make a high field magnet. Now, if you look at the material selection charts, which would be on one side the yield stress, on the other side the combination of electrical conductivity, density, and thermal capacity, you will have here the requirements for various Teslas, various fields you want to reach, and various duration of the pulse. Now, here are the materials, the candidate material that you have on these selection maps, and these materials are very often copper-based material, either pure copper, or copper reinforced with beryllium, or copper reinforced with niobium, with silver. Pure copper is very good for resistivity, but not good for strength. The maraging steel would be very good for strength, but not very good for resistivity. And again, you have to pay a contradiction between the properties. Now, one way of dealing with that is to make a composite of composites, and we'll see this example in a number of cases in natural materials again. And this composite is using, for instance, copper-niobium multi-filament structure, which will be extruded. When it's extruded, you just take the extruded fibers and you put them again together, and again, and again, and again, and you are going to have a multi-architectured structure when you go down from the nanometric scale up to the microns, or up to the millimeter, which is the size of the final cable that you try to obtain. Now, interestingly, you can have a direct relation between the yield stress and the spacing between the niobium fibers inside the copper matrix. And this spacing is, of course, related to the amount of strain that you have imposed to your composite. So you have on one side a process parameter, which is a strain, which is going to control the strength of the material, and the strength of the material simply because the obstacles are preventing the dislocation from moving. So that's the meaning of the first equation. And the second set of equation is the relation between the electrical resistivity and the material and the distance between the fibers, because the fibers are playing the role of scatters for the electrons. Okay? So again, you have a possibility to relate one process parameter, which is a strain, to the other property. And now what you have here on this diagram is a way of exploring the performance diagram by using different strains and looking at where should you strain the material, how far you should strain the composite in order to reach the point you want to reach in terms of duration of the spot of the field and in terms of magnitude of the field. Now let's go to the architectural material, which is another strategy to fill the gap. I just want to make a point of vocabulary, because people are always complaining about the difference between hybrids, between composite material, between architectural materials. I think the grammarians in Byzance were discussing about the sex of the angels, while the Turks were around Byzance. So I think we shouldn't do that. The idea is just try to see different ways of looking at strategies to improve material. The composite can be understood as a mixture of material. A hybrid material is much more controlled in a way, so some composite can be seen as mixtures, as hybrid materials. The hybrid is a combination of two or more materials in a predetermined geometry and scale, optimally serving an engineering purpose. That's coming from the PhD of François-Xavier Crom, who is in the room. Now, what is an architectural material in addition to that? In addition, we have one length scale of the microstructure of the architecture, which is of the order of one length scale of the component in which you are going to use the material. Okay? So that's what I call architectural material. Now, the question is, what is the superposition rules which govern the properties of the hybrids? And when you come to the situation of one length scale being comparable in the material and in the component, then you have an extra condition, which is what is the continuum description that can provide in that case? And I think that's still an open question. What continuum description can you provide of a material whose internal scale is not very small compared to the scale of the component in which you're using it? Now, the architectural material, that's my pet architecture material, which is the combination between conductivity and strength. What I want to discuss more now in detail is the combination between conductivity, bendability, and electrical insulation, which is this architectural material, this cable. Okay, so let's look at the general strategies to get that. You first analyze a requirement, and you look in terms of function and constraint, and try to look at what are the contradictions. So here I want to design an electrical cable combining longitudinal conductivity, radial insulation, and elastic bendability. Now there is no material which is meeting that all these conditions, and then I'm going to decompose these requirements into a number of requirements for which each of them is going to be dealt with a material, and then I will have to join the material together. So good conductors are metals, but they have a high modulus and high flexural stiffness unless they are thin enough. Now, if we look at the function longitudinal electrical conduction and elastic bendability, copper can provide that. If you look at the function longitudinal radial electrical insulation and elastic bendability, a polymer can do that. A ceramic would give you the insulation, but would not give you the bendability. Okay? Now, these two ones are going to be put in a given configuration. So instead of having one single rod, you are going to fragment that into various filaments, and that will be the cable effect. So that will ensure the flexibility. And you will have to deal with interface engineering. How can you be sure that the polymer is properly sticking on the wire? Okay? And then you can get a hybrid material. The classical electric cable is one example of this multi-material example. Now, we have seen a number of these multi-material of this architectural material in the series of lectures, and we'll see again a number of them in the second day. Now let's play with geometry a bit, which is one other of our strategies. Well, here is the simplest geometric effect you can think of, which is you want to add stiffness or you want to remove stiffness. So that's something people in mechanics have been knowing for decades. And if you read the nice books in the 50s about designing airplanes, you have a number of ways of stiffening an airplane, which is just absolutely fantastic. The imagination of these people were absolutely remarkable. If you look at the table for cables, the number of possible organization of cables in order to ensure both flexibility, bendability, strength, friction between the filaments, conductivity, heat transfer, vibration damping, and so on, is also a very huge variety. Now, there are things which are a bit less obvious, which is, for instance, when you want to stiffen a sandwich, you can put a foam inside the sandwich, which just makes the two plates sufficiently apart, one from the other, so that the elastic momentum of the section of the sandwich is large enough. That's one possibility. And to put them far apart together, you can put a foam into that, but you can also put a truss structure. And the truss structure is a very nice example of architectural material. So you have here the picture of a truss structure on the top. But there, now what you want to do when you are an engineer is you want to make a lot of them, you want to make them cheap, and you want to make them efficiently. Now here is a typical way of making this truss structure, starting from a grid like that, and that you know how to do that, and you have two punches which have the shape of a knife, and which are going to give you this structure, which is the one you want to put here. Now you see there is another problem after. If you have this structure, which is a cheap way of making this truss structure, you still have to put that into two plates, so you have to find an efficient way of joining the two plates together. And then you can think of gluing, brazing, welding, and so on. Now, I think the reason for which I wanted to show you this picture is that it's all fine to imagine very nice architectural material. You have to think of the way of making them. And we will have a number of examples which will show how to make architectural materials. The strategies of people coming from chemistry is to make them bottom up, to start from the atoms and to stack the atoms in a self-organized way in order to end with a structure. What we are going to examine here is a way to get the material top-down, starting from macroscopic aspect and trying to look at processes to get these architectures. Now, the geometries might be a bit more sophisticated. Here you have a number of pictures coming from a work by Yves Bréchet, who is the father of the interlocked materials. The interlocked material is a geometry in which the properties of the structure is given by the geometry of each blocks, the friction coefficient between each blocks, and the fact that you hold them together by an external applied load. Okay? So this material, in the general sense of the term, is a very interesting example of architectural materials because it's a tunable material. That means that when you change the way you are going to push on the side, you are going to change the whole stiffness of the structure. Now, that's the simplest possible interlocked materials. So each of them has the shape of bones. So that's called osteomorphic interlocked material. But you can think of various types of geometries, and this one might be interesting, for instance, for acoustic absorption here. They happen also to be nice, so that's why I wanted to show you this picture. Now, mixing strategy. After all, do we have to choose? Do we have to choose between playing with a microstructure and playing with the geometry? I'm going to give you a sort of overview of these architectural materials in terms of scale and in terms of ways we can combine them. Here, if you look at this diagram, the scale going from the nanometer to the meter, here you have the microstructure. That's where the people in material science have been working a lot. Here you have the superstructure. That's where the people in mechanics, structural mechanics, have been working a lot. And now between these two, in a scale which is, for the problem we are going to look at, in the scale of the micron to the centimeter, is what I call the millimaterials, just to annoy my dear colleagues who are doing nanomaterials. I love to call that the millimaterials, just to make a bit of fun. These millimaterials, architectural materials, are either coming from the microstructure with graded materials or for the superstructure by hybrid and architectural material. And the idea is in this region, we are going to have either microstructures which are at a very small scale but which are graded, which means that they are going to vary on distances which are comparable to the size of the component, or we are going to have distribution of matter which are mimicking a superstructure. So here you will find the foams, you will find the truss structure, you will find the wools, you will find the entangled material. So these bunch of possibilities are going to open a wide variety of materials. Now, here is an example. Again, I want to show that you can get an architectural material by standard processes. And this one is the process by which you can make more ductile material, which is very strong, when the ductility is limited by the propagation of cracks from the surface. If you manage by phase transformation to have a soft layer at the surface, which is going to be a sort of protection against the propagation of the crack is going to propagate inside the soft layer, and when it reaches the hard material. The crack has been blunted by its first pass, and you have material which is both strong enough because you have kept the properties of the core, and more ductile because you have killed the dangers of, for instance, the machining scratches on the component. So that's an example of an architectural material which is obtained here by phase transformation. Again, we are back to my old friends, the steels. What we are doing here is removing the carbon by annealing the material into argon hydrogenated gas, which is going to remove the carbon, and you have at the surface a layer of ferrite, which is soft by nature. Now, we don't have to choose, and I want to give you this picture, which was originally due to Olivier Boisez, which is the following. If you want to make a shaft in torsion, and you want to make it stiffer, and you want to keep it light, so one way of getting a stiffer shaft is to say, well, if you go to the material scientist, say, okay, I'm going to make a composite. Okay? If you go to a person in mechanics, he's going to say, well, I don't need to make a composite, it's a shaft in torsion, so I can perfectly take the same matter and distribute it on a larger radius with a hollow core, and that will increase the torsion momentum, and therefore, with the same amount of matter, I will have something which is stiffer. Now, you're not bound to choose between material science and mechanics. Nobody prevents you from doing both, using the geometry and using the materials and using the composite. Now, when you think of it, you still have done only half of the way here, because you have equally distributed the reinforcement along the radius here. But really, the region where you need the stiffening is the outside and not the inside. So another way is to make a gradient here in which you would have a higher density outside and a smaller density inside. And now you have to think of the process to do that. So it can be done by casting and rotating casting, in which the particle would go on the outside, and you would have a gradient which would be basically the equivalent of Perrin settling. Instead of having it vertical, you would have around the radius, and the role of gravity is simply the centrifugal forces. Now, what you have to keep in mind when you are here is that for a given set of requirements, you need, of course, to select the material and the processes, but also the microstructure and the architecture. And in each case, you need to look at what is the relation between the architecture and the properties, and what is the process which allow you to get this architecture, but also what is the relation between the microstructure and the properties, and what is the process which allows you to obtain these properties. And that's not always obvious, because the processes are very often used for bulk material, and if you go to architectural material, you are going to have material which have thinner parts, for instance. So an interesting feature is how can you develop a foam of metal with structural hardening, and what would be the heat treatment necessary to obtain the appropriate microstructure inside the structure, which in itself is already geometrical, by its geometry has different thermal properties than the bulk material. Now, let's go to more, because here I've shown you the microstructure, I've shown you the architecture, the composite, how we could have all them together. So if we go on looking at the possible strategies, I'm going to give you an example which is due to Bernard Herrieix, and on which there has been a number of studies, including by Rémi Dandievel, which is the question of thermal management in building. So you want to have a device which is able to store a lot of heat, and which is also able to release rapidly this heat. So that's basically you want to deal with the what I call the peak of the tartine le matin and of the noodles in the evening. So you want to be able to smooth out the extra consumption of energy that you are having along the day. Now what you need is, of course, a material with a high thermal inertia to store a lot of heat, but you also want a material with a high thermal conductivity to release the heat efficiently. And bang, no chance. If you look at the specific heat and the thermal conductivity, they are exactly anti-correlated. So again, we are in a situation where there is a hole in the space of material, and that's a hole we want to fill here, this one. Okay? Now, we want to have a specific heat. Sorry, you say that's not this one, that's somewhere here that we want to fill it. Now, the point is that in order to do that, the strategy is the following one. It's not simply to play with materials' properties, to play with materials' behavior. So if you want to have a high thermal capacity, one way of doing that is not simply to play on the thermal capacity of matter is also to play on the change, on the phase change of matter. That means that the latent heat of a phase transformation is going to play the role of an apparent large thermal inertia. So that's the phase change materials. And of course, the phase change materials are things like paraffin. They are not exactly good conductors. So one way of dealing with that is to embed paraffin into a structure which is thermally conductive. And one of these structures might be a honeycomb structure with metal. It might be also entangled structure like a steel wool. And then that's both of them which are going to provide you the material. And you see now the concept of material is something which is becoming very wide, the material which is fulfilling your set of requirements. Now we come to the bio-inspiration from natural material. I'm not going to talk very long about that because that will be one of the topics that both Peter Fratzel will deal with just after me, and tomorrow in an evolution viewpoint, John Dunlop will also talk about that. Now, bio-inspiration from natural material. So I just want to start by a diagram that we devised together, which is basically the parallel between the biological material and the engineering material. We have seen that in one of the lectures of the Collège de France. And the idea is relatively simple in its principle, not really easy to implement, but simple in its principle, is that nature has a limited number of elements that it can use and a limited number of processes. You are bound in natural situation to have what is called soft chemistry. You are bound to deal with aqueous solutions. You are bound to deal with polymers. Okay, the price that nature has to pay in order to get efficient structural materials is to play on the variety of architectures, on the variety of hierarchies, which is going to organize matter in such a way that the required properties are going to be obtained. So you have basically two rules, one which is to architecture at different hierarchical level the distribution of matter, and the second rule is that any material which is brittle should be in small scale. Okay? Now, another thing that nature is very able to do, and the engineers are not so good at that, they pretend they are, they try to do that. In some cases they succeed, but that's really in its infancy, which is the ability of heal the damage in the material. So I think the self-healing of material is really one major issue when we are going to go to bio-inspiration. Now, this strategy, this situation from nature is mirrored on the other side in the engineer. The engineer has a lot of elements, basically the whole Mendeleev table. It's even creating extra elements in the Mendeleev table. It's even creating plutonium for uses which are diverse, let's put it that way. But this large variety of material, of elements, is also related with a large variety of processes and access to a number of processes at high temperature, which are very interesting. Now, it's playing with a microstructure, but the variation in terms of architecture and in terms of different levels of architecturing is much less than what you can find in nature. And now you see the dream of an optimist like me, and I know Peter is probably equally optimist as I am, which is, what if we were able to merge the variety of architectures that you can find in nature, at least in its principles, and with a variety of constitutive materials that you can find in engineering. So if you can help, you can do something with both of them, you are considerably expanding the space of materials. Now, I just want to show you 3 examples, just pictures, to show you the variety of architecture. So that's a turkey tendon. When you look at the turkey in the depths of its eyes, it's really a stupid animal. And nevertheless, it has a beautiful cable structure for its tendons. Now, if you look at the bone is also a very nice example of architectural material. And the third one, which is the wood, which is well known to everybody, and the wood, again, is extremely efficient as a way of architecturing a mixture between lignite and cellulose. Now, with all these strategies that I have outlined, just to give you an overview of what we are going to see in the next 2 days, still remains the question, we want to fill holes. Is it really worth filling the holes? I go back to the basics. Back to basics is material is matter with a function. Okay? It's not simply matter. Now, is it worth filling the holes? And for instance, just to have an example, is it worth developing titanium foams? titanium, bulk material, foams, gives an architecture. What would be the property of a titanium foam? What could be the application of titanium foams? And what would be the market for titanium foams? So that what the engineer would ask to this question. So the properties of titanium foam, let's look at the virtual titanium foams. The Young modulus is going to be related to the modulus of the constitutive material and to the density of the titanium foam with the relative density with the famous Ashby-Gibson scaling law. The plastic collapse limit will be also related to the density with a different power, different exponent. The densification strain also is going to be related with the density, and the thermal conductivity is also related with the density. And all this gives you the properties of the foam, knowing the properties of the material. Here I've chosen a case which is relatively simple, which is relating elastic properties. The reason for which it's simple is that these properties are not going to be too much changed by the process of foaming. The property of the constitutive material is going to be the same. Now, if you were looking at plastic properties, the situation would be different because the plastic properties of titanium inside a foam, if you take a little bit of titanium inside a wall of a foam, might not be the same properties and will not be the same properties of the titanium in bulk form. Okay. Now, what I want to show you now is a sort of global strategy to look for possible application of a material. There are three ways of looking at that. If we think of selecting material, what you do, that you have a set of requirements, you have a database on material, and you try to merge them together. So you have a metric, which is a performance indices, and this will tell you, is this material suitable for this set of requirements? So it's more sophisticated than that, but at depth, that's basically what you're doing. Now, if you look for materials, for an application for a given material, you have to reverse the problem. You have a database of application, you have a new materials, and you want to know how this material matches to one of the applications. So that's a dream. Because just that was the third column here, which is the application match. We have worked a lot with Alexei Salimon and Mike Ashby to develop this branch, and I think that was a failure. Because to have a structured database of application is something which is extremely difficult. I mean, you cannot make a tree of that. I will probably come back to this problem one day, but right now I don't know how to deal with it. Now, another way of dealing with the problem is to make a function match, which is to say, well, this material, I can compute its performance indices, and I can look for what of these performance indices, this material, seems to be better than the 10% of the existing materials. Okay, so that's a way of saying this material is especially interesting for this combination of properties, and this combination of properties reflects a possible application. Typical case, bulk amorphous material, high yield stress, low elastic modulus, very high value of the square of the yield stress divided by the elastic modulus makes a very efficient spring. So naturally, it drives you to consider a spring for a possible application for this material. Now, the other way of dealing that is totally immoral, is what I call the cuckoo strategy. You know, the cuckoo is this bird which is supposed to go into the nest of other birds, remove the eggs, and take their seeds. Well, that's exactly what is the medium strategy, which is the material match, which is to say a new material. You want to look at how close is this new material to existing material. Now you need to define a metric for that. The simplest metric you can think of is a Euclidean metric with the space of properties, in which you would normalize the difference between, say, Young modulus by the average Young modulus of the group of material you are considering. And by that, you can look at what materials is closer to the material that you are considering. And then, for each of these materials, you can store in a database possible application of these materials. So you can say, well, my new material is close to this existing material, which is used for this application. So maybe my new material might be used for this application. Of course, you see that there is a problem there. Because if I do the distance simply a Euclidean matrix, just say I'm just looking at the difference between properties, I might find an application for which some of the properties are totally irrelevant. So that means that has to be done in an iterative way, in which you look at what material is close, you look what are the applications, look what properties are relevant for this application, and you rebuild a distance to see if it's still close for this property, and so on and so forth. So that's a way of exploring possible application. But now, just to finish the story, when you do that with the titanium foam, you have a number of suggestions which are coming, but what I just want to finish is just to tell you that one of the consequences of that is that usually when you have a new material, you don't know all the properties. But that enables you to say, well, this new material, of which I don't know all the properties, seems to be close to this other material, which is used for this application. In order to know if my material could be useful for this application, then I would need to know these properties. So that, in a way, is going to tell you what would you need to know on this new material in order to see its possible application. So if I think of a spring, if it's a vibrating spring, obviously I need things which are related to fatigue. That means that I need to study the fatigue of these bulk amorphous materials. Okay? So what I just wanted to show you here, it's a sort of tool, a systematic approach, in order to see, is it really worth filling the hole in the space of material? Now, let's go, and I want to finish by that, by an outline of the program of the colloquium. Today, we are going to have method, essentially. So starting by two overviews, the one I've just given you right now, and then Peter Fratzel is going to speak about biological material, lesson from multi-scale, multifunction, and adaptive design. So we'll start right from the beginning by having the two aspects, the engineering viewpoint and the viewpoint of the biologist. Now, we will have a presentation from Alexis Deschamps, who will explain us how to play with the microstructures and how all what we have learned by microstructure design can be used. Now we have a number of variations on the microstructures, and there will be two examples, a variation on processing and a variation on designing graded microstructure via phase transformation. So that will be Damien Fabreg on top-down processing of metallic architectured material. So that will be designing composite, I would say, architectured composites. The example that Quinn Kwan will give you is an example of designing the microstructure in such a way that you can have a graded interface and not simply a sharp interface. Now, we'll go to more than materials, because I think it's always good to look outside. And the more than material will be to look at sensors and look at a device now, simply at materials, and look at a device in which we can get inspiration from nature. So that will be the presentation of Jérôme Casas. Then we'll be playing with classical processes. That's Aude Simard, who is going to give us a presentation on using friction stir welding, which is not so classical, but still it's becoming classical in order to process new types of architectured materials. We will have a presentation also on playing with atoms and process. So that's not exactly atoms, but at least it starts from small quantity of materials which are deposited in a controlled manner. That will be the presentation on additive processing for architectured material. Rémi Danduvel will give this presentation, or Jean-Jacques, I don't know which one of both. Oh, is that you? Okay. And then we will have two examples of design. And the design will be focused on design method for multi-material, which will be given by the Bordeaux team, and design method for multifunctional sandwiches, the sandwich being the most frequent and probably the simplest of architectured materials. Now we will have after potpourri, and the potpourri is purposely disorganized. So I didn't want to have one morning on engineering material and one afternoon on biological application. I wanted to have the thing intermix so that the two communities could see what the other one is doing. So we'll start by architectured material in building, multi-material design for electromagnetic screening, which is a very nice example of associating properties, constitutive material design, geometries, and for an application which is not a structural application, which is a functional application. Architectural material in biology, so that will be our third viewpoint, overview, by John Dunlop, which will take the viewpoint of evolution. Nature is evolving, just like engineers are progressing. That's just not on the same time scale, hopefully for the engineers. Then we will have examples of architectural material for functional application by Stéphane Gors from Bordeaux. The challenge of impact tolerance would be a very interesting animal with, well, I won't tell what it is doing, you'll have the surprise. That Garrett will be giving this presentation. An example of steel-based architecture material will be coming from industry, from Jean-Philippe Mas and Olivier Boisiz. Then we will have 2 viewpoints on alternative mineralized skeleton by the teams from Potsdam, Ron Shaha, and from Potsdam and from Jerusalem, Ron Shaha and Mason Dean. Multi-materials and architecture material for medical application, then they are really at the interface because they are dealing with engineering problem for medical application. That's Denis Favier will give us this presentation. We'll go for a bit in the garden with the plant materials adaptation. The shape optimization method for architecture and material design will drive us towards applied mathematics, and this applied mathematics approach will also be used to look at the interface between different materials, and this interface between different materials, whether it's sharp or soft, has different consequences on design. So that will be Natasha Vermark from the United States and Georgios Michailidis from École Polytechnique. We'll finish with something which is close to architecture, but in the more general sense of the term, I would say. And the idea would be to look at the shape change controlled by Eigenstrain architectures. That's Sébastien Turcot from the Max Planck will give this presentation. And I think the concluding remarks will probably be without me and without you, because we will be at the end of the day. And I think the concluding remark is that we have been interested by the 2 days and we go on discussing together. I think that will be my concluding remarks tomorrow. Okay. Thank you very much for your attention, and I'm ready for any questions for the organization of the 2 days, and if not, we can go on with the next presentation. Thanks a lot. I just forgotten the conclusions. So there are some concluding remarks. The first one is that microstructure design is just one possible route for tailored materials. That was one of the messages I wanted to give you during this presentation. Second one is millimetric shape architecture are a powerful design variable for multifunctional requirement. There is an immense variety of possibilities which is opened by the combination architecture plus microstructure, and we are just at the beginning of this exploration. But it requires the development of models as guide of designing new materials. It's just an ideal playground to look at bio-inspired design, whether we take the top-down approach that I've been presenting you, or if we take the bottom-up approach, which is much more along the chemistry viewpoint on these architectural materials. There is a lot to be done and learned by a strong interaction with biology, and of course my standard motto, which is there is plenty of room in the middle. Just last picture. This is a microstructure. This is an architecture, and this is a nest. Thank you.